Hey, Algebra 1, here we are looking at logical reasoning section 1-7, and let's start off with our vocabulary. Today we're going to be talking about some logic concepts or concepts that you'll find in a logic curriculum, and we're going to first talk about this idea of a conditional statement. So a conditional statement is any statement that can be written in an if-then form. For instance, like this one, when it is late, I go to sleep. And so here's the condition. The condition for me going to sleep is that it is late. So if it's late, I'm going to go to sleep. And the thing about conditional statements is that they have the noticeable quality that they can be written in an if-then form. So I'm going to rewrite this as an if-then statement, as all conditional statements can be written. So if it is late, then I go to sleep. So this is a conditional statement written in the if-then statement form. Now the thing about conditional statements is that they have two parts. One part is the hypothesis, it is late. The other part is the conclusion, I go to sleep. So the hypothesis is usually the part that comes right after the word if, and then the conclusion comes after the word then. So the concept of deductive reasoning really starts off with a broad, I think the picture that's used is kind of like a triangle like this. You start off with a general rule, and then you go to a specific point. So you start off with like a rule, law, or principle, and then you end up talking about a specific example. So deductive reasoning would be something like this. If you need to be 16, if the law of the land is to be 16 years old when you get your driver's license, and I find out that Charlie has his driver's license, then I know he's 16 or older. So that's how deductive reasoning works, whereas inductive reasoning would be the opposite way. You start off with specific examples and then you generalize to a rule. So in math, we often go this way. We'll start off with a rule and then we'll talk about specific examples or specific things. The next idea is counterexample, and counterexamples are pretty cool because they kind of remind me of being a lawyer and say, haha, this isn't true because, and then you come up with the winning argument. And so a counterexample is an example that disproves something. So a counterexample is an example that disproves something. And here's an example. When you multiply a number by 10, the product will always have a 0 in the ones place. And so if you think this is true, great. But if you don't, I need you to give me a counterexample. So when I multiply 10 times any number, right, I need to see if I would get a 0 in the ones place. Is that always true? If I think it's not true, then I need to prove that there's a number that I could multiply 10 by, that number I'm going to put in this box, such that the answer I get does not have a 0 in the ones place. And hopefully you guys realize that the number could be like 1.1, because when I multiply 10 times 1.1, I get 11, which does not have a 0 in the ones place. So this would be a counterexample for this statement. This proves this statement to be incorrect. So here we go in example 1. We're going to be identifying the hypothesis and the conclusion in each of the following statements. So identify the hypothesis and conclusion. If it is Friday, then Madison and Miguel are going to the movies. Hypothesis, it is Friday. Conclusion, then these guys, Madison and Miguel, they are going to the movies. And it's as simple as that. I'm just going to highlight it. I'm not going to rewrite it as, you'll get it. All right. So hypothesis is going to be highlighted in this yellowy, orangey color, and conclusion will be in this greenish color. All right. Over here, hypothesis and conclusion. The hypothesis here will be the phrase or the mathematical sentence after the word if. If 4x plus 3 is greater than 27, then x, conclusion, is greater than 6. And so that's it for really identifying the hypothesis and conclusion. It's pretty easy when you have your statement written in the if-then form. In example 2, we're going to be writing a conditional statement in the if-then form. So we need to identify the hypothesis and conclusion of each statement. Then we're going to write it in if-then form. Can be a little tricky, but let's take a look. I will go to the baseball game with you on Saturday. So seems like if it's Saturday, I will go to the baseball game with you. And so with that in mind, I'm going to just highlight this with the correct colors, not the incorrect ones. Let's try that again. I'm going to highlight this as the hypothesis, it being Saturday. Then what's going to happen? I will go to the baseball game with you. And so now what I do is I'd write that down here. I think I kept saying baseball, my bad, but it is Saturday. I will go to the ball game with you. I don't know what the deal is. Maybe I want to go to a baseball game. I don't know. All right, so now we're going to write it in the if-then form. And so we do what we know to do. If it is Saturday, then I will go to the ball game with you. All right, and so that's basically what we have going on here. Let's take a look at this one. This one's a little bit different because it's mathematical in nature. So for a number x such that 6x minus 8 equals 16, x equals 4. For a number x such that 6x minus 8 equals 16, x equals 4. Well, what's the hypothesis and conclusion here? So I'm reading this that if we are in this situation where we've got a number x such that 6x minus 8 equals 16, then x has got to equal 4. And we can do a quick little bit of mental math. Throw 4 into this equation. 6 times 4 is 24. If I subtract 8, I get 16. We see that that's true. So as I look at this, it seems to be saying that this part is going to be the hypothesis. If I have this situation, then x is going to equal 4. And so I'd write that like this, and I'd write my if-then statement like this. Let's take a look at the next example. So here we're going to be using deductive reasoning. And so we're going to determine a valid conclusion that follows from the statement, if two numbers are odd, then their sum is even. So for the given conditions, and if a valid conclusion does not follow, then we're going to write no valid conclusion. So as I look at this, I'm going to check out and see if I can come up with a valid conclusion. So it says we've got the two numbers 7 and 3. Well, as I see this, I recognize that this part is an affirmation of the hypothesis here. Two numbers are odd. Yep, the two numbers are 7 and 3. That's odd. So given that, I can now have a conclusion, and my conclusion would be that the sum of 7 and 3 would be even. And I can easily check that this conclusion makes sense by actually figuring out what the sum of 7 and 3 is. We know that 7 plus 3 is 10, and indeed it's an even number. So we see that we can have a valid conclusion from this particular statement. Let's see if we can come up with a valid conclusion here. Now it says the sum of the two numbers is 14. Here, when we talk about the sum, we realize that we're looking at the conclusion. Does this conclusion give me any power over the hypothesis? I'm not sure. I don't think so. In fact, if the sum of the two numbers is 14, does it mean that the two numbers in the beginning had to be odd? Of course not, right? We could have had 6 plus 8 or 2 plus 12 or any number of different ways that we could have written this out. So the fact is there's no valid conclusion can be ascertained given the fact that we cannot come up with anything that's going to definitely satisfy our hypothesis. So there's no valid conclusion that can be made. So here an example before we get to exercise our muscles of using counterexamples. Find a counterexample for each conditional statement. If you are using the internet, then you own a computer. Well, can you think of a counterexample? I can think of one. I might just be using the internet in the library. Or I could be using the internet on my phone and I don't have a computer, or I could be using a tablet. So there's a number of different counterexamples that can disprove it. Notice we could, with the counterexample, we want to disprove the conclusion. We're going to accept the hypothesis, but we're going to disprove the conclusion. Let's see if we can do it here. If the commutative property holds for multiplication, fact, we're going to assume this, then it holds for division. Do you remember what the commutative property is? The commutative property referred to remember I said commute. Commute means to move, to travel. All right, so the commutative property says that if I have 2 times 3, it's going to be the same if I move these guys around and get 3 times 2. And we know that it holds for this, for multiplication. So does it hold for division? So we can try. What if I had 3 divided by 6? Is that the same as 6 divided by, let's make that a division symbol, divided by 3? And clearly the answer is no. 3 divided by 6 is 1/2, and 6 divided by 3 is 2, and they are not equal. So this is a counterexample that proves that, yes, this holds for multiplication, but then it doesn't hold for division. Is that all right? I hope that's making sense. Let's look at another example. All right, babies, here's our last example, example 5. We're going to find a counterexample. So you remember a counterexample disproves something. It holds the hypothesis true while proving the conclusion false. So if these two numbers divide to give you 1, then x and y have to be whole numbers. And here, 2 divided by 2 does give you 1, and these are whole numbers. This proves it, so this is not, or this supports this particular statement, so this is not a counterexample. Here, notice that with part C, the hypothesis won't be proven to be true because 1.2 divided by 0.6 does not give you 1. B, over here you get 0.25 divided into one another equals 1, and neither of those are whole numbers, and you see that this is going to be the answer, and this one doesn't work. 6 divided by 3 is 2 and not 1. So here's our counterexample. All right, I don't really love the way I taught this lesson, so if you have any questions, if you're like, I don't know what you're talking about, that's cool. Just let me know. I want to answer them. I want to discuss more. I do believe what we discussed, however, is enough for you to successfully understand and work through the problems. But if you're like, no, lady, I'm not buying it, talk to me and we can work it out and I can explain in a little more fuller detail. Take care. I look forward to talking to you guys soon.